Okay, folks, I think we're going to get started. This is Jim Toolen. I'm with Trace Environmental, and appreciate everyone taking a few minutes here. We may have some folks joining us in the coming minute or two, but in respect of the time, I wanted to go ahead and get going here. My name, as I said, is Jim Toolen. I'm the VP of Sales here at Trace. And I've been with Trace since our inception 25 years ago, and was the person that brought Trace into the ethanol industry. Subsequent to that, we deployed our CEM systems at over 60 ethanol plants throughout a region of the country. Couple brief housekeeping comments on today's presentation. Everyone is on mute except the presenters, and go ahead and knock your cameras off. We'll basically just be focused on the presentation. We're going to try to keep this as succinct as possible, so we're striving for 45 minutes on the presentation in respect for your time, and then we'll also have questions and answers as well that we'll be able to address for you. But the important thing to note is this is an introductory overview of the application and how it's solved. This presentation is not intended to make any of us experts. So I encourage you to take notes, and at any time in the future, reach out to us and we can do a deeper dive individually with each of you as you wish to discuss in further detail. So the purpose of this is to really introduce you to what we've been doing to satisfy this CO2 scrubber monitoring application. We'll discuss why it makes sense to automate your CO2 scrubber monitoring, and we will go into a little detail as to what makes the system up. So you'll see the agenda for today, basically just going to be a brief, quick overview of the offering itself. Again, my name is Jim Toolen. I'll do a brief intro here. Our lead project manager, Charles Dick, will discuss the design of the system, along with Bruce Trauger, our lead design engineer. Kevin Ramazan, who is the VP of Operations for FTIR measurements at California Analytical, will discuss the details of the analyzers. And for real-world application experience, Joe Oswalt of eEnergy Atoms will make some comments about the experiences he's had with the system and some details associated with the operation of it. Basically, this is a brief history of Trace. We began operations 26 years ago in 1995. We're currently installed at over 400 applications throughout the country, from Hoboken, New Jersey to Honolulu, Hawaii. There might be 2 or 3 states that we're not installed at, but we cross multiple industries, and we are the leading industry supplier for CEMs in 4 different industries, one of which is the ethanol production industry. You'll see also that we have personnel scattered at multiple parts of the country. Specific to you folks, we've got folks in Nebraska, Iowa, Nebraska, and Arkansas. And then we've got folks on the eastern seaboard as well in multiple states. What we do, as many of you know, is we provide continuous stack monitoring systems made up of the continuous monitoring system, the data acquisition reporting software, providing spare parts and ongoing services. For ethanol, we've deployed our CEMS for the turbines, boilers, the TO-HRSGs, as well as for CO2 scrubbers. And we provide both CEMS and PEMS, PEMS being the software-based predictive emission monitoring. The typical architecture of a CEM is important to point out because you'll notice in what Charles mentions to you that the architecture of the CO2 Scrubber CEM is very much like your typical CEM. You've got stack mounted components. You've got heated umbilicals bringing the sample back to the analyzers. Those analyzers are situated in a cabinet or sometimes in their own freestanding shelter. And then you've got the PC and software. So the CO2 Scrubber CEM is very much like a typical CEM in architecture. We also have our Web-2K software. Our legacy software -2000 was retired at the end of 2019. We continue to support it, but no longer deploy it. The Web-2K software offers the ability to have remote connectivity. So if you folks are not at your plants, but do have remote access to the network, you can work from your home or wherever you are as if you were seated at the CEM PC itself. Similarly, anywhere in the plant that has network connectivity to the CEM PC, you can work from that particular machine without requiring a copy of our software on that particular machine. So it's a very cost-effective way to work with the CEMS data and reports. In addition to the 60 ethanol plants we've installed our traditional CEMS at, we've deployed our CO2 Scrubber CEM at 10 ethanol plants. We're the only CEM company to have done so in the ethanol industry. And our real-world experience, lessons learned, directly impacts how we design the system, the components we utilize, and the way we build the system. CO2 Scrubber monitoring is a specific application that what you don't know will hurt you. So we're very grateful for the real world experience we've gotten in monitoring and learning how to most effectively design the system. As many of you know, the CO2 Scrubber CEM system is made up of analyzers, and we're monitoring parameters primarily acetaldehyde. We also monitor the VOCs by total hydrocarbons, acrolein, formaldehyde, methanol, ethanol, CO2, moisture. We also monitor stack flow for the purposes of determining mass values such as pounds per hour or tons per year. Some of the benefits that you can accrue by automating your CO2 Scrubber monitoring instead of doing your periodic contracting of stack testers is a significant reduction of water and chemical usage. By monitoring in real time, you only use that amount of water and chemical that you need in order to meet your requirements. No more, no less. Unlike stack testing, where maybe you do it during Q3 at your highest water and chemical feed rates and have to have a fixed flow from there on. Unlike that, the CO2 Scrubber CEM enables you to control those in real time and basically control your scrubber like you do the rest of your plant. For shutdowns, monitoring in real time enables you to dial back on the water pretty significantly, so you significantly reduce water buildup. You also get flexibility with your yeast and enzymes. You can experiment with those without being required to then bring in a stack tester. In some instances, you can see how much ethanol stack takes the humidity. As I mentioned before, you can eliminate stack testing for the purposes of determining your stack emissions because the system's doing that for you automatically. And then, of course, controlling the scrubber in real time.
Also, Jim, it also found some algae blooms at one point that was causing some problems for one of the customers.
And might not have known that, but for continuous monitoring. So that's a great point, Kevin. The important thing to note as well, and Joe could probably expound on this later, you're not going to be purchasing a headache. We have been very pleased to realize that the cost of ownership is quite low with these systems because the maintenance and reliability is very high, and maintenance is not beyond what you do with a typical CEM. And then, of course, the other benefit, as I mentioned before, the ability to experiment and test with your enzymes. From an upkeep standpoint, not unlike a traditional CEM, you have to undergo RADA. The nice thing about this is, particularly in Nebraska, they stretch it out to 24 months. So unlike a traditional CEM where you have to do the RADA certification every 12 months, NDEQ has moved this out to a 24-month cycle. The system automatically does its daily calibrations, and you do your quarterly cylinder gas audits. We can either do them for you or train up your operators on how to do so. And the operation remains reliable, and maintenance is very straightforward. So that's a kind of a quick snapshot of the system and some of the benefits derived. At this point, what I'd like to do is turn it over to our lead design engineer, Charles Dick, and he will go through the system and what makes it up.
Okay, my name is Charles Dick. I've talked with a number of you folks, but there's a few that I don't recognize. I've been instrumental in working with California analyzers on coming up with a system that is very similar to a lot of our systems, but there's unique issues associated with the CO2 scrubber that we've had to address. And it should be known that we're a one-stop shop, so we integrate the equipment into our cabinets. We also design and build our own flow monitor. So we're very involved in both the physical aspects of these systems as well as the IT, the DAS data collection aspects. The picture that we have right here is our standard freestanding double bay CO2 scrubber system. One of the very unique items is the fact that the temperature in the stack is much lower than a standard CEMS application, and the moisture and the sample itself must be maintained hot and wet. But first, I want to just go over the various equipment that's involved. We have the actual analyzers themselves. We have a requirement for flow monitoring. This is a sample of our wall-mounted flow unit. The insides of that flow unit, it's a pitot differential pressure type flow monitor, which is accepted widely in the industry. But in addition to the standalone cabinets, we also create temperature controlled shelters. And in many cases, when we're doing a shelter, instead of tightly packing all the equipment into a standalone cabinet, we can wall mount it, making it much easier for maintenance and accessibility. The heart of our system is our new heated sample conditioner, which we've been deploying now for about 2 years. It is self-contained, and one of the items that we found as very important in the CO2 scrubber is that the sample not come in contact with any cold points. So from the probe all the way down to the exhaust, every segment of sample handling is heated and controlled. The sample conditioner was designed to keep as much control over every aspect of the sample. It has an internal oven, so the sample never has cold spots. And the unit itself is, as I said, self-contained. We have the oven in the background, we have the heated head pump in the foreground, we have the controls to the left of the pump, and it's a self-contained unit. For anyone that's interested in significantly improving the uptime, this unit can not only be repaired quickly, but also could be exchanged quickly. So if they had the need, they could have 2 units, swap them as needed, and then make whatever repairs necessary. The basic flow diagram that many of you may have seen if you've seen our systems shows from left to right, we have equipment that's mounted on the stack. We have the extraction system, and we have the pitot tube flow monitoring system. Most importantly is the heated sample system, because that's the heart of the analyzers monitoring the CO2 scrubber. And right from the probe itself, everything is heated. Every segment is individually controlled. We bring it down to the sample conditioner, which is internally heated. And then from the sample conditioner going out to the analyzers, we have the ability to have a flow controlled output, which is required for like the FTIR. And then we can provide pressure fed heated output to devices like the THC analyzer, which will have its own internal flow control. As long as we provided adequate pressure, it controls everything from there. Our systems also give you the ability to have full calibration gas accessibility, so the automatic calibrations can be done on a daily basis, on a timed basis, so there's no human intervention necessary, but they can also be individually activated for the sake of testing and doing any calibrations, full calibrations, manual calibrations on the analyzers. The one item that we didn't have a picture of was the ZAG unit. California analyzers provide this zero air generator to clean up any instrument air that may not be adequate for measurement purposes. It's a molecular sieve that just takes out any hydrocarbons and other items that might cause interference in the FTIR readings. So that pretty much sums up our system, gives you a brief overview. If you do have any questions moving forward, we can address them in a more detailed individual method. So at this point, I would like to hand it over to Dr. Kevin Ramazan from California Analyzers.
Thank you, Charles. Well, first off, I'll talk a little bit about our company. We're California Analytical Instruments. We've been providing analyzers to Trace for over 20 years. We've been in business over 35 years, and we have over 25,000 analyzers in service. We are based in Orange, California, right next to Anaheim. So if you ever do come out and visit us, you can also visit Disneyland or Angels Stadium or the Anaheim Ducks. So we have lots of things to do around us. We have several different types of analyzers. We have our 700 series, which has an NDIR, which measures CO, CO2, methane, NO, SO2. We also have our FIDs for total hydrocarbons. We have our chemiluminescence analyzers for NOx and several types of oxygen analyzers. We also have other types of analyzers, such as our FTIR, photoacoustic analyzers, our zero air generator, and then we have a bunch of different samplers and conditioning systems, as well as full systems as well. But for the purpose of ethanol and our CO2 scrubber, they typically use our FID for total hydrocarbons, our FTR for all the HAPs that they mentioned earlier, acetaldehyde, formaldehyde, acrolein, ethanol, methanol, and CO2 and water. And then also our ZAG, which we'll talk a little bit about too. Here's an installation, one of the earlier ones. Up in the, you can see Trace puts the FID over here, our ZAG, our FTR over here. And then usually the ZAG is placed somewhere else. It doesn't need to be in the analyzer cabinet. And like Charles said, that it basically just cleans up air. So you basically put in shop air and it'll come out nice and clean. You can kind of see the back. Like Charles was saying, everything is heated. Even all the connection points have specific heater, hot pocket heaters. So everything does stay hot. So that way you don't get any condensation or any other issues that are associated with cold spots. Here's a cut sheet of our 700 series analyzer. Again, it's just a flame ionization detection device. It also is called a carbon counter. So what it does is basically burns the gas so that it measures every carbon-hydrogen bond. It's a fast response unit, and again, also operates at 191 C. And here's a picture of our zero air generator. And basically what happens in this is you send in dry, clean air, but not if it has any other components, it'll be scrubbed out. It does this by first going to a heated catalyst. The heated catalyst will burn everything down to basically CO2 or other oxidized components. And then it goes into a series of switching molecular sieves. So these molecular sieves are constantly switching back and forth, and it switches so that it basically uses one and regenerates the other one. And the purpose of that is that it has no maintenance or chemical filters or any maintenance, which is nice. It just, you put it up there and you kind of forget about it. We have some at the factory that have been running over 25 years that have never been maintained and just keep on going. Over here you can kind of see the maximum outlet concentration. So that's if it were high levels of any of those in there, it would be reduced down to less than those levels shown here. And this is basically used because the FID will need combustion air to work, and then the FTIR requires an optics purge and also requires 0 for baseline air. So this can be used for all those at the same time. Next up is the FTR. So I basically designed and built our FTR here at California Electrical. We've been selling them for about 12 years now. So we've been in the market quite a while. FTR does stand for Fourier Transform Infrared Radiation Spectroscopy. I know that's a mouthful, so here I'm kind of breaking up what all that means. So first off, the Fourier transform is a mathematical function that converts from the time domain to the frequency domain. Probably doesn't make much sense, but the key thing on this is the main calculation being involved. And back in the old days, this used to be the limitation of FTR. It would take a long time to basically calculate this for every spectrum. But now it's done in a matter of microseconds, so it's no longer an issue. Then infrared is basically light, and it's from a specific region of the spectrum. And luckily, most gas molecules will absorb here. And then we do FTR as a type of spectroscopy, which is the study of the interaction between matter and energy. In our case, we're looking at gases and light. So we're basically seeing how much light every gas will absorb. And then by taking that information, we're able to calibrate and give a ppm value for that. And then the CI-FTIR gas analyzer is utilized for hot, wet gas samples for many components. So that's important there because it does keep everything hot and wet, and it can measure many components. That's one of the key things. I mean, you may be measuring 6, 7 gases, but it could be measuring more. We have some customers that measure as many as 40 gases all at the same time.
Well, Kevin, that's a good point to raise. I mentioned earlier in the presentation, we're monitoring things like acetaldehyde, acrolein, formaldehyde, methanol, ethanol. They're all being done by this single analyzer.
That's correct. That's the beauty of it. Here's a slide I usually talk a little more about, but for the purpose of this, I just want to say we're basically using infrared light, and it has a pretty broad range of 1 millimeter to 750 nanometers. It would be great if we could use the entire infrared, but the mid-IR is all we tend to use because of limitations in optics and sources and detectors and all that. And luckily, most components have the highest absorption here. Like I said, you can measure lots of different things with the FTIR. Some of the things it cannot measure monatomic gases such as helium, argon, neon, and it also can't measure homoatomic diatomics such as nitrogen, oxygen, hydrogen. I mean, a lot of people want to be able to measure those, but it does not. It's completely transparent in the infrared, so it can't be measured. But most molecules do. For example, hydrocarbons such as the acetaldehyde, formaldehyde, acrolein, all the ones we just mentioned, they measure infrared light. Here's showing a CH2 bond, but my picture kind of came out funny here. Basically, these molecules have all these different types of motions, and each of these motions occur by absorbing light at different frequencies. So, for example, this bond here has 6 different vibration modes, which means it'll absorb light in 6 different frequencies, if not more. So basically, we can use that to be able to monitor these gases. Several of you may have used the non-dispersive infrared, and I like to compare this to an FTIR just so you kind of see the main differences. Well, both units have a similar setup. You start with an IR source that gives a broadband infrared light. Then you have some way of filtering that light to be more specific. For example, an optical filter will let 10 to 30 nanometers or wave numbers go through so that only those wavelengths will be absorbed by the gas of interest. And in the case, this is a single pass gas cell, which that's where the gas will be absorbing that light and then goes to a detector. When you go to FTIR, we basically get rid of the optical filters because a typical unit may have up to 5 filters, so that means you measure 5 gases. When you go to the interferometer, this basically has a moving mirror inside that will simulate having over 30,000 of these different optical filters. So now instead of just getting 5 data points, you're getting a full spectrum of data, which then can be used to be quantified for various gases. And we also use a multi-pass gas cell. So by having a multi-pass, you get a longer path length. And the longer your path length, the more sensitive your analyzer will be. And this sometimes requires a long path length, sometimes there's not. All depends on the requirements of the measurement. So here's some basic measurement processing. It's a lot more complicated than what I'm going to tell you, but for the basis of this, it's all you really will need to know. Like I said earlier, there's a moving mirror. So the raw data is basically a moving mirror versus a signal. And that's what you get here. So as the moving mirror moves, you get a signal. Then you basically do some processing, which is basically the Fourier transform, and you'll get what's called a single beam. So the single beam, you'll now have 2 of them. One is your baseline. So this is how much, when you do a zero gas, you have nothing absorbing there. You take that signal versus your sample signal. And you can see that there's a difference. In this case, here's SO2. So you can see there's some SO2 being absorbed. And then you'll see when you compare that to the baseline, you see there's nothing there. So by taking the ratio, you'll then get an absorption spectrum shown as over here. Of course, this shows a whole bunch of different gases because it's going to be used for so many different gases. So once you have this spectrum here, you can then use it to calibrate and quantify for the various gases in your sample matrix. Here's just a cut sheet on all the different things, kind of the key things that we've already mentioned. It measures multiple components simultaneously. You can measure from sub ppm, even ppb in some levels, some cases, to percent levels. It's typically we run it at 1 minute. It's fairly small, as you saw inside the racks. And one of the key things about this version is there's no liquid nitrogen required. It just runs nonstop, continuously, without having to add anything to cool the detector. We do have several different FTIRs. The key thing is the different path length, and then you can see down here the different response time. So typically we run at 1 minute with our main units, and then we do have some that run at 1 second, but these require liquid nitrogen. So it depends what you want to do and how you want to use it. For the CO2 scrubbers, we typically recommend our 700 FTIR because it's the longest path length, and timing-wise, 1 minute is sufficient. Here's a picture of the inside of one of these FTIRs. You can see it's fairly open, easy to work on. The key things of this unit is the interferometer, and then we have a set of transfer optics that take the light from the interferometer and then send it into a gas cell. This gas cell is 10.2 meters, so the gas will flow into here. It'll only stay in this section right here, and the light will be sent in, bounced back and forth, and then goes back into the analyzer for measurement. We do monitor pressure, and we also have a temperature sensor inside there as well, so that we can account for varying pressure changes, and we know what the temperature is inside our gas cell. Here's a picture of the gas cell showing the multi-reflection optics using ray tracing software. So you can see it bounces back and forth over 50 times. Recently, I was able to verify this with some high-powered lights, so you can actually see how the light comes in. So basically, it comes in, will hit one of these sides here, then it hits over here. You can see the brightest spot on the bottom here. Then it hits the mirror again, then hits the top, and then it comes and hits this mirror back again. And basically bounces back and forth all the way till it leaves the gas cell. This is just showing you the difference in path length. The main unit uses our 700 FTIR. You can see the has the strongest peak this is just showing ammonia at 5 ppm. But you can see the 600 FTIR still has strong signal as well for that, but you would get more sensitivity for the 10-meter path. Then here's just some example scrubber performance data. So this shows all the HAPs we measure: acetaldehyde, acrolein, ethanol, formaldehyde, methanol, CO2, and water. We also do put interference. So these are not things that you think about, but they might be in room air, such as N2O, propane, methane, and then we do also have sulfur hexafluoride often, as well as ethylene, and these are used for dilution studies if you're doing spike testing and all that. It just makes things a little bit easier to do. And over here, I basically overlaid all the common components that would be in a standard scrubber. You can see the CO2, the moisture, and all the different HAPs. But down here, I'm just showing you what acetaldehyde at 200 ppm would look like. One of the nice things about FTR is you can look up, you can basically overlay these spectra and say, oh, that's there. Or I can tell you, you know what, that matches our reference spectra. So if anytime anything looks kind of funny, I can load up spectra and say, oh yeah, I totally believe that's correct. Or I would say, there's something else there that's causing a problem. And if there is something else there, we can actually add a calibration, account for it, and then remove it from being an interferent. And also, there's multiple peaks here. So say if one's bad, like say we're blocking the strongest peak by moisture, we come over here and use the secondary peak and still get very good data. And here's what the software ends up looking like on the screen. This does everything for you. It just it'll scan the unit, get the spectrum. It does quantification, auto ranging, pressure compensation, span correction, and limited detection calculation. So it's all in one automated software where you basically just start it and do nothing. And then we actually send this data to the trace system so that it's all recorded and stored and used for trending and all that you do on site. One of the key features also is with FTR is other instruments just give you a number. You're going to have that number, and then what does that number mean? Oh, well, that's what the analyzer gave you. The nice thing with FTIR is it'll give you spectra. The spectra can be reanalyzed at any time. Like say you think something's not looking right, and we look at it and we find some other component in there, we can then measure that and tell you what that is as well. And you can have that data from whenever you've saved your spectra. And if there's any other issues you might notice along the way, we can actually analyze the spectra and say, oh yeah, that's a problem, and then fix it. These are not just used for ethanol plants. They're used for all sorts of applications. One of the hardest ones is cement. That's when you have like 30% moisture, 20% CO2. You have NOx, SOx, HCl, acid, SO2, all these different components all in the same thing, and actually damages equipment if it's not hot and wet. So for us, the ethanol process is one of the simplistic versions of using an analyzer compared to using one of these harder ones like cement. So we actually like doing ethanol analyzers since it's a little bit easier for us.
Well, it's clearly not a laboratory device, huh, Kevin? I mean, it's field proven in some pretty rugged applications.
Yeah, it's been all over. I mean, I've been to Papa Stacks. I've been to pig farms. I've been to chicken coops. All sorts of catalysts. I've been to jet engine facilities. I mean, it's one of the coolest part of my job is I get to see a lot of different applications, which is I find to be very interesting.
You mentioned, we've talked about ease of maintenance and reliability. Could you go back a few slides and look at the interior of the analyzer and what of that needs maintenance? And you may talk about this in a little bit, but what kind of replacement cycle is some of the components under?
So the number one problem we have is actually this fan. It's a very high quality fan, but for some reason they have issues over time and that needs to be replaced. That's my number one problem. I've had very few issues with the switches and power supplies and relays and temp controllers. The gas cell, usually in this application, it doesn't get damaged or dirty. There have been some situations which we were never ever able to figure out what occurs. But the gas cell is one thing that, at least that we'd have to worry about. If they have these highly reflective mirrors. But we've had fairly low issues. I know there were some early on where we had to figure out some issues, but for most cases, they retain their reflectivity very well. But if it were ever to get dirty, you would need to clean them. I've known one of the biggest issues we found is that if you turn off the analyzer when you have stack gas in there, things will condense and stick, and they don't always come off nicely when heated again. So they may need to be cleaned over time. Also, I'm not sure if various cleaning solutions run through them. I don't know if that could be the issue that damaged them as well. So usually if you're cleaning something like cleaning out your chambers and all that, you would need to make sure you are not sampling with the FTIR. And then the interferometer, that's probably the biggest portion of this. If there were any issues with that, sometimes that may be need to work on. But it's actually, they're quite rare, those issues, but they do happen every so often.
We've talked briefly about 600 versus 700 series. I guess the older version of this FTIR analyzer was the 600 series. I think Joe has that one for the last, 3, 4, 5 years. We've been going with the 700. Is the 10.2 meter path length different between the two models?
Well, that's the difference. Everything else in the unit is the same between the 700 and 600. The only difference is the gas cell. So the gas cell went from a 4.3 meter gas cell with a slightly larger volume of 800 milliliters versus a 10.2 meter, which is only 550 milliliters. So this is a smaller with a longer path length. So it's just a better gas cell.
So you're getting higher resolution, huh?
You're getting better, ppm resolution. It gets better on this unit. So yes, but that's the only difference. And we also added internal vibration dampening. That if we need to use it, you can just add a little table inside there. That's why it's a little bit taller. Just because before the vibration dampening was the feet of the unit, and that's kind of hard in a rack mount device to keep things vibrationally isolated with using feet. So that's why we put it all internal to the unit. And then I don't know if I mentioned before, it does require a purge, and that purge actually comes in here as a flow meter, and all that does is it sends zero air into the unit here and keeps all the ambient air out. So that way you don't have any influence of CO2 and moisture inside this unit on the analyzer. And also keeps it running clean. That kind of leads up to our last slide over here for us, was basically, as mentioned before, it does have low cost of ownership. One nice thing about our FTIR, it does have a laser that's a solid state laser that lasts 19 years. Others are around 2-year life, and it's a very expensive replacement and difficult to do. The IR source is a 5-year running life, which is user replaceable. I mean, it's very easy to change. Customers do it themselves all the time with just a 1-page instruction sheet. The alignment of the interferometer is permanent. The software is very easy to use, allows anyone to operate it. And then one of the key things with FTIR is the service. We provide pretty strong support, and we do that by remoting into the FTIR computer for service and training. I mean, that saves so much time and money versus sending it in or service visits. And 80–90% of the time, it's something I can log on and fix within 20 minutes to an hour or so, and I can just figure it out and get you back up and running without any issues. So that's one of the key things there. So that's all I got for you. I probably went over my 15 minutes there, but next up here we have Joe Oswald. He's the EHS manager at eEnergy. I worked with him quite a bit. He's our first ethanol installation, and I looked up the day we shipped his analyzer in 2012. So he's been a long-time user and a good friend over the years. I've enjoyed working with him.
Yeah, and I will also say, Kev, just a comment about Joe. We're very grateful that he's taken a few minutes here to give us some real-world comments on his experience with the system and the analyzers. But from a housekeeping standpoint, folks, Joe will likely answer a lot of questions before you even ask them from a real-world perspective. But if anyone would like to pose a question, that we can address at the end of this discussion, simply take your cursor and go up to the top of the screen, and you'll see the icons up there, and where it says Show Conversation, just click there, and toward the end of Joe's comments, start floating a few questions, and we could take 10–15 minutes at the end here and address them for you if you like. With that, Joe, it's all yours, bud.
Okay. Well, thanks, Jim, and thanks, Kev, for the kind words. I call him Doc. Like Doc said, and I've been working with Kevin Ramazan and Trace We were the first ethanol plant in the nation, from what I know, to install this technology on our scrubber CEMS. That was back in 2013 is when we actually brought it on the line. So then 2012 was ship and install, and I think it was March of 2013 when we first ratted this unit. So been up and running since 2013. I've been intimately involved from an EHS perspective, not only from the reporting standpoint, but this was kind of my baby when we brought it in. So I've been intimately involved since 2013 with this unit. To Kevin's point, some of the maintenance activities and things that have gone along with it, I've dug deep into these analyzers, doing maintenance activities on them, both with Trace in-house to help, with California Analytical being on site and remotely coming into the system and helping out and troubleshooting things. And I would say since installation in 2013, because we were the alpha unit, we worked through a few issues, but it wasn't anything that was a showstopper. We came together as a team, put some ideas in place, and now the analyzers since then has been working pretty well. I wouldn't say flawlessly, because I don't think there's an analyzer out there that doesn't have issues from time to time, but as flawless as possible. These units have it's top of the line system. I can't be happier with what it's done for us. And so the flexibility, when we installed our system, it was flexibility with permitting. For those in Nebraska, the NDEE, formerly the NDEQ, was big on scrubbers and being able to monitor scrubbers. And so we installed this system to do exactly that. And it has provided us with up to the minute information on emissions, on where we're at, to Jim's point, and Charles's point about, having the flow meters in place so that you can get pound per hour and then convert that to tons per year. This system does that. So you can see, pretty quickly when changes are made within the plant, you can see those emissions, how they're affected based on what changes you make in the plant. That could be your recipe, that could be water flow to the scrubber, it could be your chemical injection to the scrubber. Any number of those, this system will pretty quickly show you where you're at for compliance. So Jim did a really good job. He actually touched on most all of my points, so thank you for that, Jim. That saves me a lot of talking. Reiterate a couple of things. It was touched on quickly about remote access, and that's one of the things that I really like about this system, is the fact that I can remote access in from anywhere. So if I'm at my remote office in the Black Hills of South Dakota, for those that know me well, they know that that's what I call my remote office. I can get in there, I can see the system, I can do calibrations, I can troubleshoot, just about anything that you would normally do sitting at the computer at the CEMS unit, you can do remotely. So that is a huge benefit, being able to see that stuff and be able to address it right away. The fast response on the system, the Opus software gives you 1 minute data. So it takes a reading, correct me if I'm wrong, Kevin, but I think it's about every 15 minutes it scans and then gives a number and then takes those numbers and gives you a 1 minute number, which then goes into your calculations for your pound per hour and things. So
yeah, in 1 minute it takes 16 scans. It averages
16
those scans, and then it gives you a result. So yeah.
So then it gives you those results, and you can see pretty quickly how where you're at for compliance. So it gives you, the DAS system that comes along with this system gives you ppm, and then converts that ppm and flow then to your pound per hour. So it's a system that'll tell you real quick where you're at for compliance. When you're going through your cycles, your firm cycles, with automation, you can have the system based on how you automate it. Control water and chemical flow to your scrubber, so it makes ease of operation for your operation staff on scrubber, to be a lot less time consuming for them, I guess.
And
So,
Joe, on the water usage aspect of it, do you guys take advantage of that going into shutdowns?
we do, because you can see the flow. Flow is one of the key pieces to this system, being able to see that flow. And so when you can see flow through your scrubber, flow equals emissions. So the higher the flow, the higher the emissions. So then you need higher controls. On the reverse side, when your flows drop off, as fermentation starts to reduce and what we call fermenters dying, you can see that flow drop off, and you can adjust water and chemical accordingly, to help with water balance issues through a shutdown, a maintenance activity. So.
And Joe, you once mentioned that before having this equipment, you'd have to lock on a water level that was overly high that you'd have to rata against, and you were no longer eligible to change water and flow until you do another rata.
That's correct. Yes, with the state of Nebraska, and they have a tiered approach. I'm not as familiar with the tiered approach anymore, quite frankly, because we've had a scrubber on our CEMS for so long that with the CEMS, that tiered approach based on where you stack tested previously goes away. So if you have a valid CEMS unit on your scrubber, then those requirements for the tiered approach goes away. But if you test, and of course most people know that the state requires you to test in the third quarter, which is the hottest time of the year, and you test from peak to peak on a firm cycle, and based on that peak to peak firm cycle, then you get an average water and chemical usage, and you have to lock in either there or above that number to stay in compliance with your air permit. And what this scrubber CEMS does is it gives you the numbers immediately. You know where you're at, based on your permitting, what you have. If you have a pound per hour limit for VOCs and HAPs, then you can dial in your water and chemical to stay below those numbers. You can see that immediately, so you can adjust accordingly, and it gets you out of that third quarter rata cycle and or the tier testing based on where you tested previously. So the tier, if I remember right, had quarterly, semi-annual, and annual requirements depending on where you tested at previously. And so that is bringing in a third party to actually test your scrubber for emissions and then readjust your system accordingly. So this system gives you those numbers right away, and it doesn't get you out of the RADA testing, but it does give you a 2-year cycle on bringing in a company to test and just ensure that your system is still reading appropriately. Now, you still have your daily calibrations and your quarterly CGAs, cylinder gas audits, where you're challenging the system to ensure it's still working properly. But this RADA is just another way of testing the system against another system to see if we're reading the same numbers. And it gives you flexibility in multiple areas. Maintenance is pretty simple on these things. You got quarterly maintenance you want to be doing, and semi-annual and annual maintenance. I know Trace provides those kinds of resources. It's not hard maintenance. We've been doing it in-house just because we like to be more of a self-sufficient group. We have had Trace in to help at times also when we had issues where we needed some outside resources. So it's a team effort, overall, the systems work really well for us, and we'll continue to use it for the foreseeable future. So, like I said, Jim hit on most all of my points. I'm more here, I guess, to answer questions that people might have based on what we've seen over the last 7-8 years that we've had our system in place. So, with that, I will turn it back over to Jim.
Yeah, perfect, Joe. Thanks so much. I think we do have some questions. And again, anyone else who has other questions, feel free to submit them now. I will also say, folks, we'll be digging into some questions shortly here, but we are recording this also. So if you have colleagues or coworkers who were unable to make this, or you wish to review it again yourself, we'll be providing a link so that you can view this going forward in the future. Katie Lindblom, our marketing manager, I think, do we have some questions
We
already?
do, Jim. We have a few questions. The first question we have is, what in the system requires clean air?
Charles, Kevin, you want to take that?
Sure, this is Charles. I can take that. The clean air is used for a number of things. The primary is the burner air for the total hydrocarbon analyzer and the purge air for the FTIR. We expect the incoming air to be instrument quality air, low dew point, clean, free of grease and dust. And we use that same instrument air for our probe blowback and for the calibration checks on the flow meter. The volume is very low. We use, we're talking maybe several standard cubic feet per hour max. So it's very low volume, but those are the two items that require the clean air.
Also for zeros, for the zero baselines for the FTR, as well as zeros for the hydrocarbon analyzer as well.
Yes, and one point there is the FTIR, what they call the baseline is like the manual zero calibration. You want a very good baseline, so it requires flowing gas, zero gas for a very long period of time. So it can be done with nitrogen, but it's also a lot cheaper to do it with ZAG air. So our system allows both, and sometimes combining the two. We can purge the unit for a long period of time with ZAG air, followed by an actual reading using nitrogen. So our system is very flexible and allows us to use whatever resource we have available.
Excellent.
Another question, what problems result if the sample isn't heated all the way through to the analyzers?
Okay, one of the biggest problems is condensation. Any location along the lines where there is a cold spot, you can have condensation. The condensation, of course, being mostly water, can absorb items, and that absorption will keep it from being monitored or measured by the analyzers. The other problem is that if that condensation gets into an analyzer, it's very bad for the optics. So in order to make sure that your sample is consistent, it has to remain hot so that all moisture remains in gaseous form, and that keeps it from clinging to any surface or causing condensation and changing the actual chemistry in the sample.
Oh, what temperature should the sample be kept at?
We keep everything at 375 degrees Fahrenheit. The analyzer, the FTIR, is at 191C, but that's internal to the FTIR. Our system is capable of going to 400 degrees Fahrenheit. is the maximum for all components. So we typically run it at 375, and in a system that doesn't require that, it can run as low as 275 to 325. But every segment is individually controlled so that you can see if that there is no cold spots.
Perfect. And one guest asked, can the CO2 Scrubber CEM be integrated into our existing data acquisition software?
Definitely. The analyzers present data to our data acquisition in a very standard format. The measurements, typically 4 to 20 milliamp, are fed to our PLC. Our data acquisition system collects data from the PLC. We collect it at 1 minute intervals, and then our DAS creates long-term averages from that 1 minute data. A couple nice things is our PLC has internal historical backup. So if for any reason the DAS goes offline, communication fails, the PLC maintains that data and we can go back and recover historical data. So it's a very robust system, and any thing that needs to be added, if you can get it to our PLC in a signal that's available, 4 to 20 milliamp or whatever, then it can be added to our DAS, monitored and recorded. We also provide data to the plant. We can provide discrete outputs. So if you're going to be doing controls based on a ppm level, we can send you a 4 to 20 milliamp signal. But a lot of our systems are now using Ethernet communication. So our Allen Bradley PLCs maintain 4 data tables. 2 of them for incoming data from your DCS and 2 tables for outputs going to your DCS. And any data point that we're monitoring by the PLC can be made available so your DCS can read it directly via Ethernet or, if necessary, a discrete channel.
Yeah, so in effect, we can measure the CO2 scrubber emissions in real time, send that data in real time to the plant control system. They can incorporate it into a feedback loop, PID loop, and automate pumps or valves for the water and chemical feed. But to the question itself, we've deployed our CO2 Scrubber CEM at a number of plants that were already running our boiler CEMS or our TOHRSG CEMS, and they already had our software. So our software enables the addition of any number of additional CEMS to it. So by deploying the CO2 Scrubber CEM, as Charles indicated, we simply integrated that into the existing software and maintained separate databases of data so that there was discrete buckets of data for each of their respective sources.
And just one point of clarification. We try and make our systems so that we're only needed to intervene in the case of where you want us to change something. Jim had mentioned that we send data to the DCS. We present the data for the DCS. So in the case where your plant architecture changes and some IP address of a destination device changes, we do not send data to those devices. We make the data available. So if you make changes locally, it won't affect us. You get data from us at a given IP address, and you send data to us at a given IP address.
Thank you, Charles. Jim, there's a couple more questions coming in. The first one is there an estimated amount of time seen for ROI?
So Joe may be able to speak to this as well, and ROI, how do you get return on investment from an expense like this? Well, the potential is that through the savings of reduced water and chemical usage, you could see payback over time. I don't have a lot of data on that. Anecdotally, I have spoken to a user or two who've indicated to me that payback, the system itself was paid for in plus or minus 24 months as a function of not having to pay stack testers to come in for the purposes of determining emissions and over their reduced water and chemical usage.
Okay, and then another question, has there been a cost-based analysis of the CO2 Scrubber CEMS cost for the unit versus offset of the operational savings for optimizing scrubber operations?
So I'll refer back to my previous question. We've not done a hard poll of existing clients, to try to get those hard numbers. What I just said earlier was largely anecdotal. So we're doing our best to try to pull that together. I can only go by what's been told to me by a plant or two. So I don't have any specific numbers to share, based on feedback we've gotten or have not gotten thus far from our clients.
And I think some of that ROI is going to be based on the type of chemical you use. Again, to what Jim said, the amount of water that you have to use, even if it's through an outage, if you don't have a CEMS where you can shut water and chemical, slow it down and or shut it off once everything's finished. The other piece of that is your compliance history with your regulatory the state and what frequency you are currently testing at. So if you're required to test on a quarterly frequency, your ROI is going to be significantly better than if you're only having to test once a year or once every other year, whatever the case may be. It's really going to depend on many different factors, and that's going to be different for every plant based on, again, compliance history, water chemical usage, your suppliers for that chemical. So you're going to have to look at all of those factors when you figure in that ROI.
Any other questions, Katie?
That's all I see on my end, Jim.
Well, we do want to dig into this in a more deeper dive individually as folks feel the need to do so. So I would ask you not hesitate to reach out to us and we could address your questions specifically. Overall, I don't think we did too bad, folks. About 62 minutes on this, so we were very cognizant of taking your time. With that, this concludes our presentation, and I would like to thank everyone for joining us this morning, and I would ask everyone to please, in these COVID times, please stay well. So thank you and have a good day.
Thank you, everyone.